So,
Hello.
oh, I didn't realize I was on mute.
Hi.
Hi. Yeah, thank you so much for coming today.
Mm-hmm.
Is there any presentation or anything like that you want to test?
Yes, I guess can I share my screen?
Yeah.
Okay, yeah, and then maybe I'll check if I can get the whiteboard to work. Okay, perfect. And then let's see. So I make this full screen.
Yep. Looks good.
Yeah. Good, I can annotate directly. That's good. Okay, yeah, well, so this should be good. I don't know. How many people usually come and how long is this until?
Yeah, so usually it's about 15 to 20 people is what it's been in the past.
Okay.
Not sure if it'll be the same this week. Hopefully
Right.
it will be, probably. And then usually, so if you want to go like, I mean, around an hour plus or minus a bit. So there's pretty flexible. Under an hour and a half is the main thing. And then at the end, or just throughout, if you want to like try to make sure to ask anything you can to make it interactive, as interactive as possible, then that would be great too. So
Okay.
yeah,
And these are high school students?
yes.
Okay. Well, we'll see. I may have made mine a little too easy.
Well, it's hopefully fine. It's hard to say. I'm sure no matter what, there'll be a very wide range of ability levels.
Mm-hmm.
Hello to everyone who has joined so far. We'll be getting started in a little bit, probably 5 to 8 minutes, something around there.
Yeah, okay.
So what is your, what do you do research in?
I do differential geometry.
Interesting. I have no idea about that, but
Are you doing any sort of research?
yeah, I'm just finishing up a paper on on permutation pattern equivalences. Are you familiar with that at all?
Not really.
Okay, yeah. It's relatively simple to explain. It's just like you essentially you call two permutations equivalent if you take any. So you take some set of, for example, for the one we studied, you take any set of 4 increasing letters in a permutation and rearrange them to be some other order. And you can do that repeatedly. So then you use that to define an equivalence relation. And then you can use that to try to figure out the number of total equivalent non-trivial equivalence classes of a certain size, of permutations of a certain size, and it often ends up being quite nice, essentially.
Mm-hmm. So your main field is in combinatorics?
Yeah, that's most of yeah, mostly combinatorics. Have you been teaching online since the coronavirus?
Yes. So I teach at a couple of different schools, and each school has their own way to teach. I don't know. I don't know if any one way to teach online is as effective as the other. Well, I mean, not. I mean, better than the other. Like they all have their pros and cons of either being live or not live, if you're recorded. So
Do you prefer teaching live or recorded, or is it just you're saying benefits and downsides?
I guess I like teaching live, but I think I don't know. It depends on the student. I think there's students that will get more out of it and be more efficient when things are pre-recorded instead of live. But then the students who aren't very good at time management probably need it to be live, or else they won't really study.
Yeah, I've always found one thing that's interesting is when you do it live initially. When you do it live initially, even if you record it, then no one will actually watch the recording. But
Right.
There'll plenty of people will ask for it. But if you do it recorded initially, sometimes people do watch the recording.
Right.
This is obviously a bit different, but it's generally funny trend.
Did you used to run Math Circle in person before?
No, I actually just started this up online mainly because I wanted to try to meet the need. I did not quite a math circle, but I helped run like a local math counts club at a middle school nearby me, and some other things like that. But I didn't do like a math circle like this in person for this. Okay, so to everyone here, we'll be getting started in about 4 minutes while we let people filter in, because people can often be a little late. So people coming in. Okay, so we'll be getting started in, if anyone new has joined, about 3 minutes. Hopefully people filter in till then. So just everyone who's here, just to make sure everyone is aware, are you good with, are you able to see chat?
Yeah, it should be.
Okay, so yeah, if you're able to raise your hand and figure out how to do that, then go ahead and you can ask questions that way to everyone who's here. But if you can't figure out how to do that, because I know that's difficult, and for some reason the raise hand button doesn't seem to show up in this Zoom, you need to figure that out still. But you can also go ahead and put it in the chat, or do like a green check in the participant thing to raise your hand too. So either way, we'll work to ask questions throughout. And please ask questions if you don't understand anything. And we'll be getting started in a few minutes. Let's go ahead and get started. Sometimes a few more people filter in the next few minutes after this. So for now though, let's get started. So thank you so much for coming and giving this lecture today. And I will turn it over to go ahead and thank you again, and let's start.
Okay, so hello everyone. It's nice to meet you all online. So today I'll be talking about linear algebra. And so I'm sure you may have heard about it before, and you might have even seen it in classes, depending on how advanced you are. And today, the math that I'll be talking about isn't so bad. In fact, it's actually quite elementary. But I do want to talk about how such an easy math can get us a lot of things that we need in the real world and other not real world things. So first, what is the most complicated function or equation that you know? So anybody? Just or anything?
Go ahead, put anything in the chat if anyone has anything.
Polynomials? Riemann zeta function. Yeah, that's quite complicated. I don't really know anything about that. I mean, I know of the function, but why the zeros lie or not lie on the z or I equals 1/2 line. I have no idea. Yeah, that's pretty complicated. So do we need complicated functions or equations to describe complex systems? Maybe. I mean, here's one example. So this is what's called the Lagrangian of the standard model of particle physics. So this is all just one big function. I mean, there's an equal sign, so it's somehow an equation, but this expression is called the Lagrangian. And okay, so this is not what we will talk about today, but somehow everything that we know about in the standard model of particle physics is contained in this expression. All the 4 fundamental forces and the blah, blah, blahs. So it's quite complicated. But what about, well, what's the most, oops. Give me the answer already. What's the most simplest function that you know? Well, maybe not. So what's a function that's even more simpler than linear functions? X equals X, okay. So yes, that's pretty simple. So the term for just saying X equals X is called a tautology. So it's quite simple. I would say that maybe the most simplest function would be constant functions. So just whatever your input is, it's just output some number. Let's say 1. So can we do much with constant functions? Maybe, but maybe not. So then what's the second most simplest function? I would say is the linear equation or linear functions. So that I'm sure you've seen before. It's linear when there's only just a variable here, and the exponent here would be 1, and then this m and b are just numbers. And so the equation of a line is y equals mx plus b. If you make it a function in terms of x, then you get linear functions. So in higher dimensions, right, if we add more variables, we could still have linear equations or linear functions where we just have to make sure that the exponent on top of each of your variables is 1. So that makes things linear equations. So there's actually other kind of definitions when something is linear, but for now, in a higher dimension, ax plus bx2 plus cx3 equals d, we would call that a linear equation in 3 variables. And so if we want to work with these, maybe we might want to consider a system of linear equations. So a system of linear equations is a collection of linear equations where a solution are numbers for the variables where all the equations are satisfied at the same time. So a system of 2 equations, 2 unknowns, right? It would be something like this. 3 equations and 3 unknowns would be something like this. And I mean, you can change the number of equations and change the number of unknowns. It's still a system of linear equations. So how useful are they? I'm sure you've seen this in your algebra class before, and I'm sure you've kind of gone over a couple of different ways to solve these. Well, these systems of linear equations have a nice geometric interpretation. Basically, let's say for 2 equations and 2 unknowns, it would be the intersection of these lines, because these lines are where each of the linear equations, the variables x and y, are satisfied. So the point where they are both satisfied is at their intersection. And then a linear equation with 3 variables would be given by a plane. And so a solution to a system of linear equations with 3 variables would be intersections of planes. And with this geometric interpretation, you can kind of see the 3 possibilities for solutions to systems of linear equations. The 3 possibilities are that you have either one unique solution, right, a plane. 3 planes can intersect in one point, or you can have no solution because there might be some points where it doesn't intersect, like if you have 2 parallel planes that don't touch each other, then there are no points in common, so there's 0 solution. Or you can have, if you, let's say, have 2 points that intersect, well, then you actually have to have infinitely many points. So you have just, it's a trichotomy that you have, well, you can only have no solution, exactly one, or infinitely many. It's impossible to have just 2 solutions, two points that intersect for linear equations. Okay, so, well, they're so easy, right? They're just linear. How you solve them is pretty standard. Maybe you even learned it in middle school, where you could maybe solve for one of the variables and substitute, or you can maybe eliminate one of the variables by adding in the equations to each other. So just how much mileage can we get from these applications of linear equations? Right? Or is it just used to test you on SATs and stuff like that? Well, if we want to study mileage, then we should probably look at how cars work. And so cars work by combustion of hydrocarbons plus some oxygen. And that spits out some heat, which is energy. But then as a byproduct, you get water and then carbon dioxide, which we all want to try to avoid. So one application of linear equations is in balancing chemical equations. So for example, octane is C8H18. And well, how bad is it for our environment each time you combust one molecule of octane? Right? So in order to figure that out, we can use systems of linear equations. So the equation that we want to solve is something like this. So you're going to have x1 amounts of octane, x2 amounts of oxygen, and on this side, there will be x3 amounts of water and x4 amounts of carbon dioxide. So how can we figure out what some x1, x2, x3, x4 would be? Is, oh, okay, I already showed everything. So here's how you can apply linear systems of equations to balancing chemical equations. You would first consider a vector. Well, let's organize our data. So we have carbon, hydrogen, and oxygen. So this thing called a vector, right, it's representing how many molecules of each of these elements there are in this octane, let's say. So in octane, there's 8 carbon, 18 hydrogen, and no oxygen. And then in O2, there's 2 units of oxygen. And then for a chemical equation to be balanced, you need to make sure that there's same amounts of these elements, carbon, hydrogen, and oxygen on both sides. So water would be 0 carbon, there's 2 hydrogen and 1 oxygen. And then for carbon dioxide, there's 1 carbon, 0 hydrogen, and 2 oxygen. So we want to make sure to make sure that the equation is balanced, right? we want to make sure that this system of linear equations is solved simultaneously. And so using whatever method you learned, you can figure out that one possible solution is 2, 25, 18, and 16. And well, this is a case of when there's infinitely many solutions to your linear system of equations. Because if this equation holds, well, then you can half everything, or you can double everything, and you still get a balanced chemical equation. So any scalings of these, as long as you maintain the ratio, then it'll be another solution to the system of equations. And so to answer the question of how much molecules of carbon dioxide come out from 1 octane, well, 2 octane gives you 16 carbon dioxide. So it looks like for every molecule of octane, it spits out 8 times, well, 8 units of carbon dioxide. So not good. And if you want to apply this to any other chemical reaction equation, you would do something similar, where you set each of these positions as different elements, and then you write down how many of each are in each of these molecules, and then you balance it. So, well, a lot of chemistry, I guess, relies on just linear equations. So already, I feel like linear equations, studying these are already worthwhile. But let's see if there's other applications. So something maybe more recreational. So these are called magic squares. So what makes this a magic square? Does anyone notice anything special about these numbers and these squares? So any guesses? Well, one thing to note is that there's numbers, right? All add to this. Yes, exactly. They add to the same number. So there's 9 spaces, and there's numbers 1 through 9. There's no repetition of the numbers. And what's kind of nice is that if you add the sums of the rows, they're all the same number. It's going to be 8 plus 1 plus 6 is 15. 3 plus 5 plus 7 is 15. 4 plus 9 plus 2 is 15. But then also along the columns, these verticals, 6 plus 7 plus 2 is also 15. 1 plus 5 plus 9 is 15. 8 plus 3 plus 4 is 15. But not just that, but even the diagonals too. 8 plus 5 plus 2 is 15. 6 plus 5 plus 4 is 15. So that's what makes this a magic square. Okay, so here's a couple of questions. Is it possible to make a magic square where the sums are different? So using numbers 1 to 9 only once, and you want to have a square where the numbers add up to something different, but they're all the same. So is that possible? No. So how come?
If you want to explain it more in the chat, or you want to come on mic to explain, why not? Either is great.
Yeah, feel free to chime in, you know. This is nothing super formal. Yes, exactly. So it has to be the same number because we're using the numbers 1 to 9 only once. So that means that they all add up to a very specific number, 45. But then because each of these rows have to sum to the same thing, right? The sum of the rows has to be equal. So you just divide by 3. 45 divided by 3 is 15. So, uh, so we can only have magic squares where the sums are only up to 15. Now, is it possible to make a different size magic square? Maybe, probably. Well, how could we have gotten these numbers? So let's kind of think about how we would create a magic square for a 3 by 3, and if any other configuration is possible besides these. I mean, besides just the rotation, right? Like you can rotate these numbers or the whole entire square and you'll get another magic square. But besides that, is there some other configuration? Well, maybe not. So how can we get our magic square? Well, we can use systems of linear equations to make a magic square. So let's let a plus b plus, or sorry, let's consider this magic square with these variables. We don't know what numbers these are. Well then, what equations need to be satisfied? Well, we need to make sure that all the rows sum up to 15. So we would have a plus b plus c is equal to 15. We would have d plus e plus f is 15, g plus h plus I is 15, and then do the same thing for the columns and the diagonals. So the system of linear equations that must be satisfied is there's 8 equations and 9 unknowns. And if you solve this, then you get something called free variables. So there are variables where you have choices. So you can pick whatever number you want for I and H, and then those give you a different solution. And so at this point, you can try plugging in different I's and H's. Remember, another rule is that you could only have the numbers 1 through 9 appearing once each, and that the numbers have to be between 1 and 9. So like this number, f, we would need to make sure that h and I are big enough so that this f is actually between 1 and 9. And so a couple of these give you some conditions, like looks like h plus I needs to be bigger than 5. H here, it should be bigger than 8. And a couple, I mean, you can kind of make up your own here. So h plus I should be less than 15. And so that kind of limits how many choices you have. And so to get the magic square that I got, whoops, oh shoot. To get the magic square in the first example, you would plug in, I believe I is equal to 2 and h is equal to 9. But then if you kind of try a bunch of other different combinations that end up working, you'll notice that actually for the 3 by 3 magic squares, the only possible combinations are just the sort of like rotations of this configuration and nothing really else. And I guess that proof would be proof by exhaustion because you just try all possible I's and H's. So what about a 2 by 2 case? So let's see if that's even possible. But before we do that, I just wanted to show you a really magical square. This one is a 25 by 25. But what's even more magical about this is that if you divide them up into 5 by 5 squares, then those are magical squares too. So if you add 1 plus 4, 4, 3, 2, 3, 5, 5, 4, 7, 3, 3, 9. So actually, let me do the annotate. If you look at, let's say, this thing, and then like, let's say this thing. So each of these are magic squares as well. And all of them. So, and then what's even more crazier about this one is if you square each number, it stays a magic square, where it's 25 by 25. So this, I mean, you definitely needed a computer, but the equation that you would set up would be very, very similar to a equation that we set up for the 3x3 case. You'd have 25 times 25, so 625 unknowns, and lots of equations, especially because of these sub 5x5 restrictions. But before we move on, let's study the 2x2. So let's try to think of a 2x2 magic square. I mean, I know that there's only 4 numbers, so you can just by exhaustion try all combinations. But let's try to use linear algebra to find if there are any magic squares for a 4x4. So the equation that we would need to solve is, well, actually, first of all, if there was even a magic square, then what number would it need to be? So using the same logic as before, it would be 1 plus 2 plus 3 plus 4 divided by 2. So 5. So we would want to make sure that a plus b is 5. We'd also want c plus d to be 5. Yeah, let me write it like this. And we also want a plus c to be 5, and b plus d to be 5, and a plus d to be 5, and b plus c to be 5. Well, you can start trying to eliminate variables, but you can be a bit more systematic about this and plug it into what's called a matrix. So here, we write down the coefficients. So there's, in the first equation, there's 1 and 1 and 0 and 0. And in the second equation, it would be 0, 0, 1, 1. And in the third equation, there's 1, 0, 1, 0. And the fourth equation is 1, 0, 1, and 0. And then this would be a plus d would be 1, 0, 0, 1, and 0, 1, 1, 0. And then these are all equal to 5, so I'll just put 5s here. Okay, so now what we want to do is do a process called row reduction. So this is basically like eliminating variables, but we're being very systematic about it. What it is we'll want to eliminate these variables first. So get rid of all the a's, so get a on its own. And so to get rid of this, what you would do is you would multiply this equation by -1. and then add it into this equation. So then what you would get is 0 for A, and then you would have minus B plus C equals 5 minus 5 is 0. So this middle equation becomes minus B plus C equals 0. So we need to change that over to here. So this becomes uh, 0 and minus 1 and 1, 0 and 0. Okay. And the point of doing it like this is that we don't need to be writing these variables over and over again. What is important are the coefficients. So we're just going to do it all over here instead now. So if we subtract, so let's see. I still haven't really thought of the best way to do this is, and maybe in the interest of time, I just punt to a computer. Oh, no. So if we subtract 1 from here, we'll get, whoops. We'll get 0 here, negative 1, and 0. So 0, negative 1, 0, 1, and 0. Looks good. And then we can repeat the process, but instead, now we want to get rid of the B variables. And so we can basically take one of these rows, I'm going to pick this because it looks the nicest, and add it in or subtract in to get rid of these other numbers. So if you add this in, you would get 0, 1, 1, and 5, and 0, 0, 2, and 5. And then here you'd want to subtract it. So anyways, you'd still get 0. This is still 1. You get minus 1 over here and 0. But anyways, so maybe I'll just skip a bunch of steps. What's going to happen is that you will get a matrix like this. So how do I, oops, one moment. Okay, here we go. So here's this calculator, and I think there was 6 equations and 4 unknowns. So there should be 5 here. And it was 1, 1, 0, 0, 5, and 5's everywhere here. And 0, 0, 1, 1, 5, and then A plus C, and B plus C, and A plus D, and B plus C. So when you kind of keep doing this row reduction thing, then you get, oh geez, oh, it outlines all the steps for you. Something like this. So it tells you that the only possible solution is, or sorry, I shouldn't, why is this the only possible solution? Okay, so once you row reduce, then you get this matrix here, which if you rewrite in equation form, this is saying A equals 5 over 2, B equals 5 over 2, C equals 5 over 2, and D equals 5 over 2. So in this 2 by 2 case, we cannot get a magic square because we don't have any freedom in choosing other numbers as before. We don't have a free variable. So we just have this one unique solution, which is all 5 over 2. But that's not a magic square because the rules for a magic square is that it needs to be numbers from 1 to 4. So it looks like there is no magic square for a 2 by 2 case. And so you can kind of see how tricky constructing magic squares might be in general. So it's actually kind of a topic that is sort of explored on with magic squares, of whether there even is a magic square for every n, and like how many different unique ones, like besides just rotating them, there are. And so they're quite magical. And so now you can kind of see how difficult it must have been to conceive of this thing. I mean, not just using linear equations, but even kind of being brave enough to attempt it. But still, the math behind finding these, so if you want to tell a computer how to find it, is just using linear equations. Okay, so we already sort of talked briefly on this, but it's instead of writing out our linear equations with the variables over and over again, we can write out this system of linear equations in what's called matrix form. So these blocks of numbers are called matrices, and the number of kind of horizontals you have are your rows, and the number of the verticals you have are the number of columns, and you would usually refer to them by row times column. And you can multiply a matrix to a vector by defining multiplication as you multiply the row by the column. So you would do this number times this number is AX, plus this number times this number is BY is equal to E. So if you've seen this stuff before, then it should remind you of dot products. And then the second equation is going to be CX plus D. So you do row times column. And so studying systems of linear equations is the same as studying matrices, sort of, in some sense. And so now how about applications of matrices? And also, I guess, why is this called linear algebra? So we can define an algebra with these matrices. So instead of kind of looking at this matrix as a bunch of separate numbers, kind of view this thing as a whole, and then you can define things like, what does it mean to add two matrices together, and what does it mean to take their product of two matrices? So the word algebra has a more precise definition, um, but just kind of the key part is that you can add matrices and you can multiply matrices under some conditions. You can't just take any matrix together and add and multiply them together. But I guess the multiplication we sort of talked about is by row times column, and we will use that. So let's move on to another application. So this one is in an application in a branch called graph theory. So has anyone heard of the movie Good Will Hunting? Is everyone too young, or I don't know, has more better taste in movies? I thought it was a good movie. Well, anyways, so this is a problem that popped up in that movie, Good Will Hunting, and it's supposed to be some unsolved problem, I think, but it's not an unsolved problem. It's actually pretty easy. And so anyways, imagine you have a map of a railroad system. Each of these edges is a certain train that connects these two stations. And in this one, they can go both ways. And let's say that between two stations, it just takes 1 hour, like all of them. So they're all uniformly like distanced. And for stations 2 and 3, there are two different trains that you can go. So you can, I guess, go this way or this way, forward and backwards. And so now the question is, in 5 hours, how many ways are there to go from station 1 to 4? In exactly 5 hours. So you can't just go from 1 to 4 and then wait 4 more hours. You have to take exactly 5 hours to go there. So then one possible way would be to go from 1 to 2. So let's see, 1, 2, 3, 4, 5. So in 4 hours, you can kind of go explore these stations, come back, and then in the last hour, go here. Can you go around this thing twice? 1, 2, 3, 4, 5. So you cannot. And then I guess there's two choices, right? If you go here, you could have gone this way or that way. Maybe you can go 1, 2, 3, 4, 5. Yeah, you can go from 1 to 2, 2 to 4, 4 to 2, 1 and 4, like that. But anyways, it's kind of complicated, right? So is there a way to count the number of ways to go from 1 to 4? Well, you can use matrices. I mean, you can use systems of linear equations to actually compute this. So what you have is something called the adjacency matrix of a graph. So how do you compute this? Is you just count in 1 hour how many different ways are there to go from station I to J. So here's 1, 2, 3, 4, and 1, 2, 3, 4. Okay, so in 1 hour, in exactly 1 hour, because you have to go somewhere, there's 0 ways to get from 1 to 1. And then there's 1 way to get from 1 to 2, so 1. And then there's 0 ways to get from 1 to 3 in 1 hour. You have to go to train station 2, right, first. So that's impossible, so 0. And then there's 1 way to get to 4. And then from 2 to 1, there's 1 way. From 2 to 2 is 0. From 2 to 3, there's 2 ways. And from 2 to 4, there's 1. And then from 3 to 1, it's impossible. But 3 to 2, there's 2 ways to go, right? You can take this train or that train. 3 to 3 is 0. And then 3 to 4 is also impossible. And then from 1 to 4, so 4 to 1, there's 1 way. And 4 to 2, there's another way. and 4 to 3 is impossible, and 4 to 4 is impossible. Okay. So then, if we call this matrix A, then let's try to compute A squared. That is A times A. Sorry. So
While we're doing this, I just want to see if anyone knows what essentially we're doing here, or why exactly this works. Try to think about that while we're doing this, and if you have it, put like a green check up in the participants list, or try to put it in the chat, and it'll be great if someone wants to try to explain that and why this is going to help us answer the question.
yeah, very good. And the hint is write out the linear system, and you'll see. Well, I don't know if it's super obvious, but you'll want to write out the corresponding linear system of equations. Okay, so we do row times column. So it'll be this row times this column. So 1 times 1 is 1, and 1 times 1 is 1 again. So 1 plus 1 is 2. And then this row times this column will be 1. And this will be 2 and 1. And then this row times this column is 1. And this row times this column will be 1 plus 4 plus 1. So it's 6. Yeah, that's right. And let's see, this will be 0. And this will be 1. Yeah, 1. Then just need to do a couple more. So this will be 2 and 1 and 0 and 1 here. And then let's see, row 3 times column 3 is 4. And row 3 times column 4 is 2. So this is 2. And the last one is also 2. I used a little bit of a shortcut called, well, we used a little symmetry, which if you haven't seen this before, I'll go over it in just a second. But okay, so we have this matrix. So, okay, let me try to do this. Okay, get rid of this. And then be very careful not to erase what I have. Okay, yeah, we're all getting used to how to use Zoom. So you have these numbers. What do these numbers mean? Well, this is A squared, and what this gives you are the number of ways to get, handwriting's terrible, to get to stations I to J in exactly 2 hours here. So from 1 to 1, there's 2 ways. You can go from 1 to 4 and then back 4 to 1, right? So that's one way. Or you can go to 2 and then to 1, and that's the only way. From 1 to 2 in exactly 2 steps, it would be, you'd have to go from 1 to 4 and then 4 to 2. Right? You can't go to 2 or you're stuck. So it looks like there's a lot for 2 to 2. I guess you can go this way, 2 to 2 in 2 hours. Let's see. So you can go this way and this way. That's 1 and 2. Wait a sec. Okay, and then you can go here and here. That's 2. And then you can go from 2 to 2. Okay, see, there's so many because you can, so you can go here and back, here and back. You can go here and then take the same train back, or here and take the other train back, and here and take the same train back, and go here and take the other train back. And so that's that. So in order to answer this question, 5, what you want to do is basically compute A5, or multiply this 5 times. So this is A times A times A times A times A. And you would do this row column thing. So of course, by hand, it'll take a long time, but you should plug it into a computer or a calculator, and it will tell you how many ways there are. And so for this system where we can go both ways, it'll give us a symmetric matrix. That is, if you noticed, that if you reflect this matrix about here, right, then it's the same thing, right? And that's because if you can get from I to j, then you can get from j to I. So, and symmetric matrices have their own other like special properties that you could learn later on. But you can compute this adjacency matrix for directed graphs. So if your graph has a direction, then it won't be symmetric, but it'll give you the same conclusion. So this is kind of leading on why this thing works to the next topic. So that's actually pretty good. But to give you this like kind of rough around the edges answer, let's say this is A, B, C, D. All right, then the linear system of equations is B plus D, and then we'll just put a question mark here, and A plus 2C equals something, and 2B equals something, and A plus B equals something. So on this side, let me put capital A, B, C, D. This A is not the same as this A. So what is this equation telling you? It's telling you how many ways there are to get to this number A, right? And how many ways there are to get to this number B and to get to C and D, right? So one way to kind of think about this is that to get to, instead of like thinking about like number of ways to get to 4, or no, sorry, a number of ways, I mean, so instead of thinking like, okay, one has, it could go to 4 and it could go to 2, you want to think like, okay, how many ways are there to get to 4? And there's 1 plus 2, right? So in order to get to this place, you have to get to either here or here first. And so if you count the number of ways to get to 1 in however many steps, and then count the number of ways to get to 2 in the number, however many steps, like -1, your penultimate step, then if you add the number of ways to get to these two together, then you would know the total number of ways to get to 4 in however many steps. So you think sort of inductively. So sorry if the explanation was kind of crap. But you can learn all about it in graph theory. It's It's actually a pretty important topic, uh, even if you're not going to go into like pure math research, because basically, like station number two seems very popular, right? Because there's lots of ways to get to station number two. It's like a hub. So it's like if it was an airport, right? It would be like Chicago or LAX, where you have to take flights from a small town to this nice station, and then you can go somewhere else. So station two is very popular, right? And so um, well, the idea with these Google search engines is to figure out who is the most popular. And so what they thought of was, in a very rough way, um, a website is more popular if it has more links to it. I don't really know if it's still like this. I mean, because computers kind of have advanced a lot more since like 2000 or whenever Google started. And also, I think there might be some politics involved, like Facebook. I don't but the page rank, like Google algorithm thing, is a real thing, and there's a research paper to it, and that's the gist of it. And even Google uses just linear algebra to rank uh, the popularities, and so they construct an adjacency matrix, except that their adjacency matrix is probably like a billion by a billion or even more. Yeah, probably much more. And so computing that is kind of crazy. And so the reason why Google is able to get so popular is because they researched a mathematical way to compute uh, that ranking really, really fast, back in the days when internet was really, really slow and computers are really slow too. So that's a little advertisement to study linear algebra. Uh, and now in the last few minutes, let me kind of say a little bit more. So another kind of thing that linear algebra studies is vector spaces. And very roughly, it's a set of objects that when you scale or add two things in the set, it stays in that set. So a typical vector space that you might imagine is something like this, right? So the classical example is a bunch of these arrows and directions, and that if you define addition of these arrows as go here and then there, and wherever you end up, that's your new arrow. That's vector addition. And then this entire, let's say, plane would consist of a vector space, because if you add two things on a flat piece of paper, then they kind of stay on a flat piece of paper. It doesn't go above it, or there's no kind of like height to these vectors. So that's a vector space. But there are other vector spaces as well. For instance, oh, whoops, too fast. Like the set of polynomials is a vector space. And in fact, the set of polynomials of a certain degree is a vector space, because if you add two quadratic polynomials, it's another quadratic polynomial. And if you multiply a quadratic polynomial by a number, it's just another quadratic polynomial. So it doesn't have to be these arrows to be a vector space. So well, we'll get to that. We'll talk a little bit more about that. And a mapping between vector spaces to vector spaces is called a linear transformation if it does one more thing, which is that if you add the vectors and then transform it, it's the same as if you transform the vectors, then add it. And the same thing if you scale the vector and then transform it, it's the same as transforming the vector, then scaling it. So that's a linear transformation. And so the big thing with linear transformation and matrices is that all linear transformations can be represented. All linear transformations between finite dimensional vector spaces can be represented by a matrix. So don't worry too much about the word finite dimensional here. Just that linear transformations and matrices are related because Well, all linear transformations can be represented by a matrix. So here's an example that I wanted to get to. So suppose you have degree 2 and degree 3 polynomials, or spaces of polynomials, then they are vector spaces. So there's a linear transformation between these two spaces that you may or may not have seen before, called differentiation. So if you don't know what it is, then don't worry. It's just a thing. But if you have seen it before, then you'll be impressed to know that you can represent a derivative of a polynomial by a matrix. So this is your matrix. So why is this representing the derivative? Well, first we have to think about how to represent the polynomial. So let's say x cubed plus 2x plus, or maybe square, plus 1, right? So this polynomial, we can represent it as a vector by just writing down the coefficients. So this, I may have messed up actually. It might not be this, sorry. No, that's right, yeah. So this can be represented by the polynomial 1, 2, 0, and 1. So it's this because the coefficient in front of x cubed plus 2x squared, right, plus 0x plus 1 times the constant term, right? We just copied down the coefficients here, 1, 2, 0, and 1 here, in this order. So if you take the derivative of this guy, then it becomes this polynomial, 3x squared plus 4x plus 0. So in the space of degree 2 polynomials, we can describe it as 3, 4, 0, because there's no constant term here. So now what happens if we do row times column of this polynomial, right? So d times this polynomial is going to be, okay, I think I did mess up. So sorry, it's not this matrix. It should be 3, 0, 0, 0, 0, 2, 0, 0, 0, 0, 1, 0. Yes, that looks more correct. So I added the 0 column in the wrong place. So let's do matrix multiplication here of 1, 2, 0, 1. Then it's going to be 3. And then this is going to be 0 times 1 is 0. 2 times 2 is 4. Then the rest are all zeros. And then these, right, the only number that would matter is here, but that's a 0 there. So 3, 4, 0. So by matrix multiplication of this matrix to this vector, we showed that this polynomial transforms to this polynomial. So the derivative is a linear transformation between vector spaces of polynomials. And it's not just that we got lucky. If you try it for other ones, if you know what a derivative is, you can do it like that. So I guess the novelty for this is if you were, I don't know, maybe making a computer program and you only dealt with certain polynomials of certain sizes, then instead of programming the derivative like function, you can just define it as a matrix multiplication, and it's probably a lot quicker computationally. So these are just some of the applications of linear algebra. So thank you all for your time and attention.
Thank you so much for coming today. And I hope to see everyone next week. I'll be sending out an email soon about the topic for the next lecture. So I hope to see you all then. Thank you so much for coming, and thank you for giving a lecture today.
Mhm.